So I will be talking about Wasserstein index of dependence for Bayesian non-parametric modeling. And to give a brief outline of the talk, I will start with some introduction to my field of study, which is Bayesian non-parametrics. I will be describing two fundamental concepts, which are the one of derive process and exchangeability. And then we also mention how to go beyond both the derive process and the exchangeability assumption. That being said, I will pass on to the core of my work, which is to find measures of dependence in Bayesian non-parametrics, and in particular using optimal transport theory through the Wasserstein distance. So I will be describing a first work together with Antonio Lévy and Igor Prunster, and then also how we developed this work into the creation of an index of dependence between 0 and 1, also together with Hugo Lévy from Bocconi University. Finally, I will be describing some future research directions, which concerns the creation of an hypothesis test of homogeneity across different groups of observations. So first of all, I would like to thank my co-authors, Hugo Lévy and Antonio Lévy and Igor Prunster, all from Bocconi University. So Hugo is an expert in optimal transport, whereas Antonio and Igor are experts in Bayesian non-parametrics. So it has been quite fun to find some research exchanges between these two different areas in such a way that it could be of interest from both perspectives. Okay, so let's start with the most simple Bayesian model that one can think of. So we have observations that are IID conditionally on a parameter. And this is coupled with the choice of a distribution for the parameter, which is called the prior. Now, traditionally, there is distinction that one often makes between parametric and non-parametric models. And this basically has to do with the space where the parameter lives. So when the parameter is finite dimensional, so when it takes values in Rd for some d, then we talk about parametric models. Whereas when the parameter space is infinite dimensional, so for example, taking values in the entire space of probabilities, then we say that the model is non-parametric. So for example, one of the simplest non-parametric models one can think of is where you have the parameter being equal to the entire distribution of the data. So basically, you assume that the observations conditionally on this random probability are IID from the probability itself. And then you simply have to choose a prior for this random probability. And one of the most notable choices is the derive process. So for those of you who are not familiar with the derive process, so I guess that at first, when one thinks about specifying a law for a random probability, it kind of seems as a cumbersome concept. But then when you look at the derive process, you can really see it as an intuitive specification. So first of all, these random probabilities are almost shortly discrete, so that in practice, it suffices to specify the law for a set of atoms and a set of weights, which of course have to sum up to 1. And with the derive process, this specification is quite straightforward. So the atoms will simply be IID from a given base probability measure. And then as for the weights, so their specification is a bit less straightforward because of the fact that they have to sum up to 1. So they are independent from the atoms. And then one can actually specify their law in a sequential procedure, which is known as stick breaking procedure, which I guess it's quite easy to grasp. So first of all, we know that the weights have to sum up to 1. So they will also have to lie between 0 and 1. So we take the first weight from a beta distribution whose support is 0, 1. Then once you have picked the first weight, you know that the remaining weights have to sum up to 1 minus pi 1. And so what you do, you simply pick another beta random variable and multiply it by 1 minus pi 1, so that you're sure that the second weight will lie between 0 and 1 minus pi 1. And so basically you can continue in this way with a third weight and so on. And what one can show is that this leads to a sequence, an infinite sequence of weights that almost surely sum up to 1. Okay, so this is just an example of a non-parametric model. And in this talk, we will focus on non-parametric models. So from now on, we will deal with this kind of assumption where we have that the observations conditionally on a random probability measures are IID. And this is coupled with the choice of a prior for the random probability. For example, we can think of the derive process, but this is just one particular case. And well, using this non-parametric assumptions in the model is actually giving a lot of flexibility to our models, because indeed you are not restricting to one particular functional class for the distribution of the data. And so one can make this flexible inference by analyzing the posterior probability of the random probability given the data. And well, if you look at this kind of models, you can very easily see that this entails exchangeable observations in the sense that their law is invariant with respect to permutation of the indices. And actually, also the converse holds true. And this is Definiti's theorem, which tells us something stronger. That is that for any exchangeable sequence, one can actually prove that there exists a random probability measure such that the observations are conditionally IID given this random probability measure. Mm-hmm. So this is to say that exchangeability is a very intuitive assumption of homogeneity in the data. And it can be seen as somehow a Bayesian equivalent of the frequentist IID assumption. So as for the specification of the law for the random probability measure, we saw that the leadership process is one option, but it is not the only option. And well, there are many ways to specify the prior for random probabilities. And what many procedures have in common is that they can actually be seen as a transformation of an underlying random measure with a particular structure, which is called a completely random measure. So completely random measures are easy to define. So basically, we are only asking for the random measure to satisfy this assumption. That is, that if you evaluate it on disjoint sets, then you get independent random variables. So if you restrict to R, this is actually equivalent to asking for the independence of the increments, basically. So just a few words on completely random measures, since they will have an important role in the rest of the talk. So one can prove that completely random measures are almost surely discrete. So basically you just have a set of jumps and a set of atoms. And the law of a completely random measure is actually given through the specification of a Lévy measure, which describes the intensity measure of an underlying Poisson random measure, which basically describes the joint law of the jumps and the atoms of the completely random measure. So in practice, whenever you want to specify the law for a CRM, it suffices to provide a Lévy intensity. Okay, and as for the kind of transformation of completely random measures that you can find in the literature, well, there are many possibilities. I'll just mention a few, which I believe are the most common ones. So first of all, you can take a normalization of the random measure, so to obtain a random probability measure. And one can actually show that if you start from a gamma completely random measure and you normalize it, you go back to finding the Dirichlet process. Then another way of using completely random measures is through kernel mixtures, which allow to model both the density functions or hazard rates, depending on your final object of inference. And finally, a common specification is also through an exponential transformation, which allows to model survival functions. So, summing up what we said until now, very often it is reasonable to assume that the order of the data does not influence their distribution. And so in such case, one of the most intuitive models would be to assume that the observations are conditionally IID given a random probability measure. And to specify the law for a random probability measure, you can actually take a transformation of an underlying completely random measure whose law is specified through a Lévy intensity. Now, what happens very often is that data come with covariates. So in such cases, one typically wants to introduce some form of heterogeneity in our models. So for example, if we consider the case of a categorical covariate, so that you basically can think of your data as coming from different groups, for example, here I just took 2 groups for simplicity, then one can actually extend the previous model in a very straightforward manner. So for example, we can actually say that the data in the first group conditionally on a random probability measures are IID. Then we take another random probability measure and say that the data in the second group conditionally on it are IID. And then we just introduce the dependence between the 2 groups by taking dependent random probability measures. And of course, if you look at the specification of this model, you see that whenever the 2 random probabilities are equal almost surely, then we basically go back to the model at the beginning of the slide. So we're back to full exchangeability assumption. Now, the nice thing about this class of models is that once again, we have a definiti type of theorem, which actually tells us which kind of invariance we are characterizing through these models. And indeed, one can prove that these models are equivalent to asking for partially exchangeable observations, which basically means that you can permute the order of the random variables belonging to the same group. So for example, here on the example on the left, we are permuting x1 and x2 that belong to the same group. So we know that the distribution of the vector will stay the same, and this translates an idea of homogeneity within the same group. Whereas on the example on the right, we are permuting x1 and y1 that belong to 2 different groups, and so we are not guaranteed that the distribution will stay the same. And this translates an idea of heterogeneity across different groups. So the idea here is that partially exchangeable models are really ideal whenever you have distinct groups of observations that you believe are somehow related. So you want that the observations in the first group tell us something also about the distribution of the second group and vice versa. And the question becomes, how much borrowing of information do we want across different groups? And well, turns out that this is encoded in the dependent structure between these vectors of random probabilities. So we can think of 2 extreme situations. When the random probabilities are independent, there will actually be no borrowing of information across different groups. And this corresponds to the case where you have independent groups of observations. On the other hand, as we said before, when the 2 random probabilities are equal almost surely, so when they are maximally dependent, you will also have a maximal borrowing of information. And this corresponds to the situation of fully exchangeable models, which are the ones that we introduced in the beginning. So this is to say that when you consider partially exchangeable models, it's really important to elicit the prior dependent structure in your models, since it will have a huge impact on the borrowing of information you are actually implying. Now, There have been many proposals in the literature on how to model this dependence among random probabilities, but there haven't been many attempts on how to measure it. And this is the question that we addressed in this work with Antonio and Igor. So basically, we focus on a broad class of models where you actually model the dependence between random probabilities in a two-stage procedure. So first one models all the dependence at the level of an underlying vector of random measures with independent increments, mu1 tilde and mu2 tilde. So these vectors, which we call completely random vectors, are exactly the multivariate equivalent of the completely random measures we introduced before. And once again, we can actually show that these completely random vectors are almost surely discrete, and they will have a common set of atoms and some related dependent jumps. So once again, when you want to specify the law for a completely random vector, we can actually do that through a Lévy intensity. But now the Lévy intensity will actually be a multivariate one, since it will account for the distribution of the common atoms and the different jumps. Then, once all the dependence is introduced at the level of this underlying completely random vector, one then applies a component-wise transformation T, such as the ones that we saw before, so to obtain a vector of dependent random probabilities. And so basically we wanted to find a measure of dependence for this class of models. And we wanted to satisfy a certain number of properties. So first of all, since all the dependence is introduced at the level of the random measures, we wanted to find a measure that was valid irrespectively of the choice of transformation T. Then we also wanted it to be naturally extended to more than two groups of observations, since, of course, in general, categorical covariate come with more than two levels. And we wanted to find an expression of this measure of dependence in terms of the hyperparameters in the model, in such a way that then we could actually use the measurement of dependence to elicit these hyperparameters in our models, so to induce the right amount of dependence in our models. And of course, by doing so, we wanted to go beyond the current state of the art, which simply consists in these measures of pairwise linear dependence. So the approach that we have used is a distance-based approach. And so I will briefly describe the main idea. So first of all, once again, we focus on these vector of random probabilities that can be expressed as component-wise transformation of an underlying vector of random measures. So the first idea has been to recast the problem of measuring dependence at the level of this underlying vector of random measures. And we observed that whenever the two random measures are equal almost surely, so whenever they are maximally dependent, we were actually going back to the assumption of fully exchangeability of our model. So basically, we can picture exchangeability as this diagonal, as supported as in this diagonal line in the graph. And then our idea to measure dependence was quite simple. So we thought of measuring dependence in terms of distance from the maximally dependent scenario. So distance from exchangeability or this diagonal line in the graph. And well, in order to do so, we had to introduce a distance between these vector of random measures, which, as we said, we call completely random vectors. So the results that we achieved in this work have been to, first of all, define the first tractable and informative distance on completely random vectors that is available in the literature. Then, since we wanted to compute this distance in practice, we actually found tight bounds of the distance in terms of the Lévy intensities of these completely random vectors, since, as we said, in practice, when you want to specify the law of a completely random vector, you're only given the expression of the Lévy intensity. And finally, we use these bounds to measure dependence for well-known models in the Bayesian non-parametric literature that are built on completely random vectors. So I'll just say a couple of words on the distance that we considered between completely random vectors. So in principle, the definition is quite intuitive. So basically, we considered the set-wise evaluations of the completely random vectors and took the Wasserstein distance between the set-wise evaluation. And then we simply took the supremum over all Borel sets. So here, the Wasserstein distance is the Wasserstein distance between the probabilities in R2. And well, for those of you who are not familiar with the Wasserstein distance, I think it's a very intuitive distance in a way. So basically, if you have to compare the law of a random variable with respect to a fixed point, then probably one of the most intuitive thing to do is to just take the expected value of the difference between the random variable and the fixed point. But now, if you want to compare the law of two random objects, you would then probably think of taking the expected value of the difference between the two random variables. Yet, in order to compute this expected value, you need a notion of dependence between x and y. But since you're only given the laws of x and y, you don't have a natural way to consider a dependence structure between x and y. And then what you do is that you simply take the infimum over all possible dependence structures between x and y, which are usually called the couplings between the law of x and the law of y. So what is really nice about the Wasserstein distance is that it takes into account the underlying geometry of the space. And this makes it ideal whenever you have to compare distributions that have different support, which is actually our case, since, as we said, exchangeability is actually a degenerate distribution on the diagonal line. So in practice, we have to compare distributions with different support. And well, in this scenario, most common distances, such as total variation, Hallinger, or even like Kullback-Leiber divergence, do not give an informative notion of discrepancy. Okay, so once we have defined the distance, we said that we also found some tight bounds in terms of the Lévy intensities. So I just would like to say a few words on the kind of bounds that we found. So for this part, I will be focusing on homogeneous completely random vectors, which basically means that the atoms and the common jumps are independent. Okay, so this is just for simplicity, but the theory holds also for the non-homogeneous case. So from now on, I will be focusing on this raw measure, raw Lévy measure, which describes the law of the jumps of the two random measures. So raw is a measure supported on the upper right quadrant. And whenever it is degenerate on the diagonal, one can actually prove that the corresponding assumption on the observation is actually exchangeability. Now, rho can have both finite or infinite mass in principle, but it turns out that in most applications in the Bayesian non-parametric literature, it has infinite mass around the origin. But if we were to consider Lévy measures with finite mass, then one could actually prove that the corresponding completely random vector has a compound Poisson distribution. So the idea here is that one can actually approximate any completely random vector with a compound Poisson distribution by simply removing a neighborhood of the origin. And so by performing this compound Poisson approximation, our completely random vectors, we were able to find this very general bound of the Wasserstein distance between completely random vector with a quantity that only depends in an explicit way from the Lévy intensities of the completely random vectors. So indeed here in this expression on the right, you find the Wasserstein distance between two distributions. And here the distribution is the one that you obtain by basically removing a neighborhood of the origin and just finding the normalizing constant. And one can show that this probability distribution is actually the distribution of the jumps of the compound Poisson approximation of the completely random vectors. Very well, so now that we have a quantity that depends in an explicit manner from the completely random, from the Lévy intensities, then we were actually able to compute it in explicit examples in the literature. So just to give you a flavor of the kind of results that we found, I will briefly describe them on compound random measures, which are a very nice and effective way to model the dependence between completely random measures that has been introduced by Jim and Fabrizio in 2017 in a JRSSP paper. So the idea is pretty simple. I guess one takes, first of all, a baseline completely random measure, so with jumps ji and atoms xi, and then one perturbs the jumps in two different directions depending on the random measures. So now I'll stick to one particular example of compound random measures, which is probably the most used one. So basically one takes the baseline completely random measures to be a beta completely random measure, and then one uses independent perturbations for the jumps distributed as a gamma. So the very nice fact about this specification is that you have a hyperparameter phi that only influences the dependent structure between the random measures without actually impacting on their marginal distribution. So you can actually see phi as a hyperparameter only adjusting for dependence. On the other hand, since phi appears both in the baseline completely random measure and in the jumps, it is not easy to understand how it impacts the dependent structure. And well, thanks to our techniques, we were actually able to bound the Wasserstein distance from exchangeability with a quantity that depends explicitly on this hyperparameter phi of the model. And well, of course, one of the first questions that one may ask is whether our bounds are tight. And for the moment, we only have empirical proof of this happening. So for example, in this graph on the right, you can see first of all, in red, the simulated Wasserstein distance, so which corresponds to the quantity on the left. And then in blue, you can see our theoretical upper bounds, which correspond to the quantity on the right of the equation. And you can see that these quantities are quite tight. Okay, then we have similar results, but I will not be dwelling too much on them for additive models, which basically are another effective way of modeling the dependence between completely random measures. And once again, we can see that our theoretical upper bounds are very close to the simulated ones. And so this is actually concluding the first part of the talk. So basically, the main contribution of our work with Antonio and Igor have been to, first of all, introduce for the first time a distance between completely random measures and completely random vectors, which I believe can be of use in many other contexts in Bayesian non-parametrics, also beyond the measurement of dependence. And then the second idea is the fact that to measure the dependence between these infinite dimensional random objects, such as random measures, then probably one of the most intuitive way to do so is by introducing a distance. Now, at the same time, our work also left some questions open. So first of all, the first question is about this upper bound that we found in terms of the Lévy intensities. Because it is true that our distance between quantity random vectors was very intuitive, but at the same time, when it came to evaluating it analytically, we were only able to evaluate this upper bound. And so we thought, well, is the upper bound a distance itself? Because in such a way, we could actually preserve the notion of distance from exchangeability, but in such a way that we are actually able to evaluate it analytically as well. Then the second question was the following. So I guess that using the distance from exchangeability to measure dependence makes a lot of sense whenever you want to compare different dependence structure. So you would say that one completely random vector is more dependent than another one whenever it is closer to exchangeability. But at the same time, you cannot answer questions about the absolute quantifications of dependence. So for example, saying, does a completely random vector have an intermediate dependent structure? And this is because we do not know, in principle, what is the maximum possible value of the distance from exchangeability. So these are the two questions that we addressed in this very recent paper with Antonio Igor and also Ugo Lavenon from Bocconi University. And so as for the first question about the upper bound, well, the difficult part in proving that this is a distance comes from the fact that we have an expression in terms of a limit, and this makes proving the non-degeneracy property of distances particularly difficult. And so what we began thinking of was that maybe we could actually avoid this limiting expression by thinking of this limit in terms of an optimal transport problem directly at the level of the Lévy measures. And basically, we spent a couple of months defining this distance at the level of the Lévy measures, which seemed to be particularly interesting because these Lévy measures have infinite mass around the origin. So we were actually considering a distance between measures with infinite mass. And we proved many properties. And after a while, we just realized that it was a special case of an extension of the Wasserstein distance that was already defined by Figali and Gilly in 2009. So the thing about this extended Wasserstein distance is that indeed it allows to compare measures that have different mass and possibly also infinite mass, which, as we said, is actually our case. And just to give you like a hint of what kind of distance this is. So I'll just say a few words on the case where the Lévy measures are supported on the real line, so between 0 and plus infinity. So as we said, these Lévy measures typically have infinite mass around 0. So what is a coupling here of two Lévy measures? Well, it will be a measure on the upper right quadrant, basically, such that the push forward map of the projections coincide with the two Lévy measures, ρ1 and ρ2 respectively. So this is nothing else but the measure theoretical equivalent, let's say, of the joint distribution having fixed marginals. And then once we have defined the notion of an extended coupling, let's say between Lévy measures, we can actually define this extended Wasserstein distance in the same way. So basically taking the infimum over all possible extended coupling of the difference between x and y, which is exactly the measure theoretical equivalent of taking the expected value of the difference between x and y that we saw before. And for example, we actually proved that when we are dealing with Lévy measures on 0 plus infinity, we also have the expression of the optimal coupling. So basically, this will now be expressed in terms of the tail integrals of the Lévy measures. And it actually comes in a very intuitive form. That is, the extended Wasserstein distance is actually equivalent to the L2 distance between the generalized inverse of the tail integrals. So in a very similar form to what happens with random variables in R. Okay, so this was just a bit of an excursion on this extended Wasserstein distance between Lévy measures. But now in our context, we are not dealing with one-dimensional Lévy measures, right? Because we are looking at multivariate Lévy measures. So once again, in principle, we do not have the expression of the optimal transport coupling. So we wanted to find the maximum possible value of the Wasserstein distance from exchangeability. And as you can see, this actually involves solving an intriguing max-min problem. Since, as we said, the Wasserstein distance can be expressed as the infimum over all possible extended couplings, and then we want to find its maximum value. And well, in order to solve this problem, our main ideas have been two. So first of all, since we want to find the maximum possible value, instead of looking at the expression of the Wasserstein distance as an infimum over all possible couplings, we thought of considering the dual formulation of the extended Wasserstein distance, where you basically have the supremum over all pairs of Kantorovich potentials. And then once we had this dual formulation of the extended Wasserstein distance, we found the expression of the optimal pair of potentials, which by no means it's an easy task in general, because it is actually equivalent to finding the expression of the optimal transport coupling. But in our context, we were actually able to do so because we are looking at the Wasserstein distance from exchangeability, so from the diagonal. And since this diagonal has a degenerate support, so it is actually supported on a one-dimensional space, the problem becomes easier. So once we found the expression of the optimal pair of potential, we were actually able to show that an upper bound of this expression is found whenever we take the Lévy measure to be supported on the axis. So the maximum distance from the diagonal is actually a distance supported on the axis. And well, it turns out that whenever the Lévy measure is supported on the axis, then the corresponding completely random measures are independent. So putting these two things together, we were actually able to prove that the maximum distance from exchangeability is achieved under independence. And well, yes, I guess that this is one of those examples where basically having an intuition of what your result should be helps you a lot in finding a proof. But then again, these are two fundamentally different tasks. And well, thanks to this maximization result, we were then able to create a Wasserstein index of dependence, which was our final goal since the beginning, between 0 and 1. And this Wasserstein index of dependence enjoys some very nice properties. So first of all, it measured dependence for an arbitrary number of random probabilities. And moreover, it is equal to 0 if and only if the corresponding random variables are independent among different groups, whereas it is equal to 1 if and only if the observations are fully exchangeable. And once we have this Wasserstein index of dependence, as we said, we can actually compute it in practical examples in the literature. So here you can find it with compound random measures and with additive random measures. And so, and you can see how it varies with the hyperparameters of these models. And so to answer the initial question of when does a completely random vector have an intermediate dependent structure? Well, now that we know that the Wasserstein index is between 0 and 1, we can just say that this happens whenever the index is close to 1/2. So for example, with compound random measures, this happens when phi is close to 1, whereas with the additive random measures, this happens when z is close to 1/2. And so I guess that this index is then can then be useful to fix the hyperparameters of the model, so to induce the desired level of dependence in these models, but also, for example, to choose hyperpriors for the hyperparameters. For example, by centering these hyperpriors around a specific value of the dependent structure. And then I also think that an interesting application of this index can be on what concerns model comparisons between Bayesian and parametric models, because then basically you can actually take different priors, different completely random vectors that induce the same dependent structure a priori, and then see how these models perform on the data. Okay, so then summing up, so what we saw today is how to define a distance between completely random vectors and how this distance can be used to measure dependence in Bayesian and parametric models. And then we brought up the case that in order to perform absolute quantifications of dependence, you actually need an index between 0 and 1. And by solving a max-min problem, we're actually able to find this index. And now, as for future directions, we would actually want to investigate what the data tell us about the dependent structure among different groups. And so our idea is then to use this Wasserstein index of dependence to actually perform an hypothesis testing of homogeneity across different groups. Because as we said, the idea of homogeneity is actually captured by the notion of exchangeability. So we could actually perform a null hypothesis of exchangeability and reject the null hypothesis whenever the Wasserstein index of dependence a posteriori is bigger than a certain threshold. And I guess that having this distance-based test for partially exchangeable models is would be a particularly important alternative to current methodologies, basically because most common models for partially exchangeable data actually give 0 prior mass to the null hypothesis of exchangeability. And so basically introducing a distance is actually a way to extend the use of these models, not only for inference and predictions, but also for hypothesis testing of homogeneity. Okay, so this was it. I'll leave you with some references, and thank you again for being here.